Hello, this is Anthony with Copley. Today we'll be talking about an interesting application request. Or a question about an application. Um, this came in an email this morning. Working on a wire welding application. It has a dual axes. It's a BE2 and connected to a linear motor actuator. Both axes have to move at the same time until each actuator touches the wire and then set an output to weld. I need to be able to move both axes and monitor the following error of each axis. When the following error exceeds a certain amount, it means that they've touched the wire and they need to stop motion for that axis. We can't weld until both axes touch the wire, so we need to be able to monitor the following error for both axes simultaneously while in motion. Is this possible with CVM? So yes, this is possible with CVM, so you're going to be checking the following error for both axes. So it's an AND condition, right? So the following error exceeds certain amount so the following error parameter has to exceed the following error limit, and then you have a following error generated on that axis. So condition 1 is the following error for axis A. Condition 2 is following error for axis B. And then when both of these are true, we'll get the output. Output 1, we'll just set output 1 as an example. So if this, then set this output. So I'll show a software solution in CVM, but then we'll also test the response to a hardware solution also using CVM. So here's the software solution in CVM. First sequence 0 will just start moves, velocity and position mode, moves for axes A and B. Then we'll jump to sequence 1, step number 1. We'll get the parameter A4, which is the latching fault status register, and we'll save it. So for each axis we'll do that, and we'll save it to R1 for axis A and R2 for axis B. And again, A4 is the latching fault status register. So it's this register that has all the faults in it, right? And we only care about one of the faults. We only care about bit 9. So we'll do a little trick. The logic being, we're going to AND that value now in R1 with 0x200, which is bit 9. So that way we'll know if bit 9 is set, then we'll have this 0x200 value in the result R3. And likewise R4 for axis B. So we'll have these conditional jump steps check if that, so again, if we just think back to, 0x200 is really 512 in decimal, so that's what that number is. So if we get 512, so if bit 9 is set, meaning do we have a latching, do we have a following error for axis A, then we're going to jump to sequence 2, step number 3. If we have a following error for axis B, then we're going to jump to sequence 3, step number 3. And if neither of those, then we're just going to continue back to step number 1 for this sequence, continually polling in this loop. So let's say that first we get axis A has a following error. Well, if axis A gets a following error, then the move will abort. So we'll only need to start polling axis B, right? So we're going to jump to this this sequence, step number 3, and we're just going to see, okay, did axis B get a following error? Because axis A already did. So if we do have a following error, then we'll jump to sequence 4, step number 1, which is just setting an output. And if that's not true, haven't gotten the following error yet for axis B, we'll just continually jump back here and get that value. And then jumping back here, likewise for this step, if axis A hasn't gotten the following error but axis B has, then we'll go to sequence 3, step number 3, and we'll check axis A this time and continually pull axis A until both have gotten that following error, and then we'll just jump to this set output sequence. So that's how you would check those two conditions, yeah, so that's the software solution. Next thing we'll do is test this and see the timing. Okay, so now I'll test the CVM sequence. Hit the play button, record. Okay, so we can see there that I just generated following error with just by putting some resistance against the motors, but see here the response time is, let's see, what is that? From where? Right there, 36225, and so it looks to be about, let's see if I can do that out. Looks to be about 3 milliseconds, roughly, which is good. So we got like a 3 millisecond response time. Now I'm going to test a hardware solution and see if we get a better response time. Alright, so now we'll look at the hardware solution. The BE2 has high-speed outputs, these encoder outputs, so it has on the axis A, we have an S and S0 channel, so here, this is pin 33, and then the S0 is pin 18. So, and then likewise for axis B, S0 and S. We're going to be using the S0 channel and for both axes, because when the fault is active, the S goes low and the S0 goes high. So these are obviously, S and S0, those two are inversions of each other. So, so we're going to tie 24 to pin 8, in 2, and then we're going to tie 18 here to pin 7. And so just tying inputs to outputs can make this a nice solution for us. So so yeah, these two states will be high when we have both of the faults, those following error faults. So the CVM sequence becomes very simple. You start the move, and then you just wait for this input mask. We don't care about the other inputs. We're just going to wait for these two, in 1 and in 2, to be high, and then we'll set the output. And yeah, so that's how you would do this in the hardware. So I'm going to save this and start it. So both motors are jogging now, and so I'll begin to record. So you can see there they both went high, and the output also went high. So if we can zoom in here and look at this response time, that looks a lot better. Let's see. Looks to be about 2 milliseconds. So we shaved off a millisecond response time by instead of implementing a software solution, going with a hardware solution. So so yeah, that's how you two different ways of you can simplify your program a little bit, and yeah, hope this was helpful.